discuss about D and F block elements of class 12 chemistry. To have a good knowledge about this topic, you should have basic knowledge of electronic configuration from structure of atom, chemical bonding and periodic table, periodicity in properties. If you have basic knowledge of this, you can get through this chapter very well. So let us start with D and F block elements. Now what are transition elements? In D block, D subshell is filled, and in F block, F orbital is filled. Now transition elements means the properties undergo a transition from metals to non-metals through these elements. So the metals or elements which are kept in the middle of the periodic table are D block elements and are called transition elements. Let us have a look at the periodic table. Here in the middle we have D block elements. In the first series, scandium to zinc, 3D orbitals are being filled. In the second series, yttrium to cadmium, 4D subshell is being filled. Here 5D orbitals are being filled. So we have 3D, 4D, 5D and 6D series in D block elements. Now at the bottom of the periodic table, F block elements are placed. We will see the general electronic configuration of transition elements, that is D block elements. The general electronic configuration is written as N-1 D 1 to 10 NS 0 1 2. Now all the D block elements are classified, namely 3D, 4D and 5D series. (3D, 4D and 5D, 6D series corresponding to the filling of 3D, 4D and 5D or 6D orbitals. Now we will see general characteristics of transition elements. The transition elements are metallic in character. Now all these elements are metals. This is because the number of electrons in the outermost shell is only 2, and even the d orbitals are incompletely filled. Now we will have a look at the electronic configuration of the D block element. This is the first series, scandium to zinc element. Now first you have to see the outermost shell is 4th shell, S orbital is being filled here. Just observe, all the S orbitals are occupied by 2 electrons except chromium and copper. Except chromium and copper, in these 2 elements S orbital is filled by single electron. Now you should have all the noble gas elements in mind: helium, neon, argon, krypton, xenon, radon. This belongs to first period, second period, third period, fourth, fifth, sixth. Now the element, noble gas element before this is argon. So we can write the general electronic configuration for first transition series as the inner core is represented by argon, and here the 4th shell, the s orbital of 4 shell is filled by 2 electrons. 3D, this is the number of electrons here 18, here 2, 20 it comes. So in scandium, the atomic number is 21. So the one electron is occupied in the 3D subshell. Now here it is 22, 3D2, 3D3. In chromium, D4 is not found, it is D5 because the energy level for S and D orbital is very small. So this becomes half filled, which is more stable, and in 4s we have only one electron. Note this point. And then continues 5, 6, 7, 8. Here in copper again it is not 9, it is 10, D10, and in 4s orbital we have one electron. In zinc again it is 10 and 2. So completely filled and half filled orbitals are more stable. So we find variation in the electronic configuration. Similarly, in the next series, 4D series this is, that is 4D subshell is being filled. In 4D series again we find few exceptions. One electron in Nb, Mo, Tc, ruthenium, rhodium. In palladium it is 0, so we have written the general electronic configuration as Ns 0, 1 or 2. Now again in silver it is 1, rest show 2 electrons in the s orbital. Now the noble gas we have to take here is this. Like this we can write the electronic configuration of each series. You have to know the variation of configuration in each series. So that is about writing the electronic configuration of D block elements. Suppose write electronic configuration of the element which has atomic number 26, then you have to write, it is a simple trick is 20 after 18, 26 comes, 18 is argon, electronic configuration of noble gas argon, and these 2 electrons 4s2, 6 electrons 3d6. Now while removing electrons, we have to remove electrons from here first, then d orbital. So general electronic configuration over. Now we will see general characteristics of transition elements. First we will see metallic character. All these elements show metallic properties like hard, high melting point, boiling point, tensile strength. All the metal properties are shown by these elements because they have unpaired electrons in d orbital and the outermost shell contains 1 or 2 electrons. And strong metallic bond is formed. Next property we will see melting and boiling point. Transition metals usually have very high melting point and boiling point due to the presence of strong metallic bond. Strong metallic bond is possible because of the presence of unpaired electron. In zinc, cadmium and mercury, metals have lower metallic lower melting and boiling points as they have completely filled d orbitals, because of which no unpaired electrons are available, and unavailability of unpaired electron leads to lower melting point and boiling point, and metals do not undergo covalent bonding. Next we will move on to atomic and ionic radii. Atomic and ionic radii. Now, as we move from left to right, atomic number increases, same time nuclear charge also increases. Now the atomic radii of 3D series, that is from scandium to zinc. First decreases. This property we have studied clearly in long form of the periodic table. First decreases, that is from scandium to chromium, it decreases. Then from chromium to copper, it remains almost same. Then from copper to zinc, it increases. Now here, the decrease of atomic radii or size is due to increase in nuclear charge. Nuclear charge increases, so the size decreases. The radius remains constant from chromium to copper, that is because almost constant, that is because nuclear force is equal to screening effect. So here almost radius remains constant. Here screening effect is more due to electron-electron repulsion in the d orbital. So size increases. Size increases from copper to zinc. In 4D and 5D series, the radius is almost nearly same, that is due to lanthanoid contraction. Next we will move on to ionization energy. If we know the radius of an atom, we can explain ionization energy of that. The ionization energy of transition elements are higher than those of S block elements but lower than P block elements. In a particular transition series, ionization energy although increases gradually as move from left to right, but this increase is not appreciable. Since the size decreases from left to right, ionization energy increases from left to right, and we find some variations here. Now first series, second series, third series, the ionization enthalpy is given and it is against number of d electrons. We find some exceptions there, that is due to variation in the electronic configuration. Next property is color. Transition metal compounds show color in contrast to those of S and P block elements. The color is mainly observed due to the absorption of radiation and by the electrons, and these electrons undergo transition, DD transition they undergo. So while coming back to lower energy state, electrons emit radiation. These emitted radiation show color. So the color, different color shown by different metal ions in their aqueous solutions or with other ligands are shown here. Next, another property is they form alloys. Alloys are homogeneous solid solutions of two or more elements obtained by melting the components and then cooling the melt. When the components are melted and cooled, we get alloy, that is mixture of two or more metals. Metals blend together to form alloy. This is because since transition metal have similar atomic radii, they form alloys very readily. Interstitial compounds. Transition metals form number of interstitial compounds in which they take up atoms of small size like hydrogen, carbon and nitrogen in the vacant spaces in their lattices. The presence of these atoms result in the decrease in malleability because the vacant space present in the lattice structure are occupied by some small elements. So they lose their properties like malleability, ductility, but hardness increases, due to which melting point also increases, tensile strength also increases. Next property is catalytic property. In most of the reactions, transition metals acts as good catalysts. So the reason for this is they show variable oxidation state and they provide large surface area. Now oxidation state, variable oxidation state and large surface area, because of these properties they are behaving as good catalyst. Next property is complex formation. The transition elements have unparalleled tendency to form coordination compounds with the Lewis bases, which are called as ligands. Now in transition elements we find large number of vacant d orbitals. So these orbitals are available for bond formation with the ligands. So they form complexes. Example for some of the complexes. Next, one more property is variable oxidation state. Now all the elements show variable oxidation states depending upon the number of electrons available for bonding. Depending upon the number of electrons available for bonding in their S and D subshell. The energy levels of 3D, 4D, 5D orbitals are very close to, that is 3D is very close to 4s, 4D is very close to 5s, energy of 5D is very close to 6s. So electrons from both ns and n-1d orbitals can be used for the formation of bonds by transition metals. Now, if ns electrons are involved in bond formation, then we get minimum number of oxidation state. If both n-1d and ns electrons take part in bond formation, then we get maximum oxidation state. So minimum and maximum oxidation state is obtained by the electrons of ns and n-1d orbitals. So minimum oxidation state, all the transition elements except chromium, copper, silver, gold and mercury have a minimum oxidation state of +1 and +2. Maximum oxidation state, each of the elements in the group 13 to 17 can show the maximum oxidation state equal to its group number. This should be 3 to 12. For example, chromium in group 6 shows a maximum oxidation state of +6 and dichromate ion also. So +6 oxidation state is shown by chromium in chromate as well as dichromate ion. And in 3D series, manganese shows highest oxidation state +7 and ruthenium and osmium have a maximum oxidation state equal to +8, which is the highest oxidation state shown by any element. We can have a glance over oxidation state of different elements. So scandium +3 and we have maximum oxidation state shown by manganese, that is +7, and from here onwards the oxidation state decreases. So here number of unpaired electron is high. So as we move from left to right till the middle of the series, number of electron increases, number of unpaired electron increases. So that is the reason for oxidation state. And next property we will see, magnetic property. Now on the basis of behavior in a magnetic field, how the substance behaves in the presence of a magnetic field, we classify the substance as paramagnetic, diamagnetic and ferromagnetic. Now paramagnetic substances, they have unpaired electrons, so they are attracted by magnetic field. Diamagnetic substances do not have unpaired electron, all the electrons are paired, so they are repelled by the magnetic field. Whereas ferromagnetic substances are special type of paramagnetic behavior. They are strongly attracted by the magnetic field. And the magnetic property is represented by magnetic moment, and it is calculated by the formula mu is equal to square root of n into n plus 2, where n is the number of unpaired electrons, where n is the number of unpaired electrons. The unit used is Bohr magneton. Properties of potassium permanganate. Before that, we will see the preparation of potassium permanganate. Now, potassium permanganate is prepared from pyrolusite, treating it with a base in the presence of oxidizing agent. Potassium manganate is formed, which on acidification forms potassium permanganate. Here we can see MnO4 2 minus, when treated with an acid, gets converted to MnO4 minus. Now this in alkaline medium forms MnO4 2 minus. MnO4 minus on treating with an alkali gets converted to MnO4 2 minus. Note this. Now potassium permanganate is a powerful oxidizing agent. So oxidizing properties depends on the medium, that is acidic medium, basic medium or neutral medium. In neutral solution, it acts as moderate oxidizing agent. Now in neutral medium, potassium permanganate is converted to MnO2, note this point. Some oxidizing properties of KMnO4 in neutral medium are: thiosulfate is converted to sulfate, sulfide ions are converted to sulfur. Then in strong alkaline medium, potassium permanganate is converted to, just check the reaction here, alkaline medium, potassium permanganate is converted to manganate ion. So the reaction is MnO4 minus is Mn converted to MnO4 2 minus. Then iodide in alkaline medium is converted to IO3 minus, iodates. Then in acidic medium, Mn plus 7, that is the oxidation state of Mn in KMnO4 is plus 7. So in the presence of an acid, potassium permanganate is converted to Mn2 plus, Mn2 plus. So based on the medium, we get the product. Just go through this thoroughly. Now we will check preparation of potassium dichromate. Potassium dichromate, not like preparation of potassium dichromate, we will see. It is prepared from chromite ore by treating it with sodium carbonate in the presence of excess of air. We are getting Na2CrO4, that is sodium chromate, which on acidification forms sodium dichromate. This sodium dichromate is more soluble in water, so this is treated with KCl to get K2Cr2O7, that is potassium dichromate. Again note, CrO4 2 minus in acidic medium gives Cr2O7 2 minus. CrO4 2 minus in acidic medium gives Cr2O7 2 minus. So Cr2O7 2 minus in basic medium gives CrO4 2 minus. So just like potassium permanganate, potassium dichromate is also a powerful oxidizing agent. So it oxidizes Fe2 plus to Fe3 plus, Sn2 plus to Sn4 plus, iodides to iodine, like that. Next we will move on to F block elements. Now in F block, the electrons are filled in F orbital. This is cerium to lutetium, which is following lanthanum. These 14 elements are known as lanthanoids. They are known as lanthanoids. So lanthanoids, differentiating electron enters 4f orbital here. These are cerium to lutetium. The name lanthanide is because they come immediately after lanthanum. Next series is known as actinides. In actinides, the differentiating electron enters 5f orbitals. These are thorium to lawrencium. So these elements come immediately after actinium, so the name is actinides or actinoids. Now we will move on to electronic configuration. In D block elements, the valence electrons are entering penultimate D orbital. Here anti-penultimate F orbitals are being filled. So this gives the period number n-1 D subshell. In that subshell we find 0 to 1 electron, and in F orbital we find 1 to 14 electron. Now just before this, the noble gas element present is xenon with atomic number 54. So the inner core is represented by xenon, 4f, 1 to 14, 5d, 0 to 1, 6s2. This is the general electronic configuration of lanthanides, and for actinides the noble gas element is radon. 5f orbital is being filled, that is 5f 1 to 14, 6d 0 to 1, 7s2 is filled. We will have a look at the electronic configuration of the lanthanides. Now the thing you have to note is, in all the elements, 14 elements, the s orbital is filled by 2 electrons. While writing electronic configuration, keep in mind, in all the 14 elements, the s orbital have 2 electrons. Then the penultimate shell, d orbital, has either 1 electron or 0 electron. Now you have to keep in mind in which d orbital there is 1 electron, rest you can assign 0 electron. So first one is lanthanum. D1 configuration is shown by lanthanum. Then cerium. After that it is gadolinium and lutetium. These 4 elements show D1 electronic configuration. If you keep this thing in your mind, you can write the electronic configuration very easily. So these 4 elements have D1 configuration, and remaining all the elements have D0 configuration. Now F is filled based on the atomic number. So atomic number of xenon is 54. To that s electrons 2 are added. 54. So atomic number of xenon is 54, all the s electrons are 2, then based on the atomic number add electron in the f orbital, and d electron is either 0 or 1. So if you keep all these points in your mind, you can write the electronic configuration of lanthanides, electronic configuration of lanthanides. So we have here cerium to lutetium lanthanides, which follows lanthanum element, so they are called as lanthanides, and the noble gas element is, before lanthanum the noble gas present is xenon. Next we will move on to atomic and ionic sizes of lanthanides. Atomic and ionic radii of lanthanides decrease with an increase in atomic number. This gradual decrease is known as lanthanide contraction. Because of the lanthanide contraction, the radii of the elements of 3D transition series are very similar to those, third transition series are very similar to those of second transition series, that is 4D and 5D series show almost nearly same atomic radii. This is because of lanthanoid contraction. This is because of lanthanoid contraction, because of the poor shielding of 4f electrons. Poor shielding of 4f electrons. Now lanthanides exhibit the oxidation state, common oxidation state +3. Some of them also exhibit the oxidation state of +2 and +4. Cerium 4 plus F0, in that state it attains the configuration of noble gas, which is highly stable, and europium 2 plus F7 we get, which is half filled, again stability is more, and ytterbium 2 plus F is 14, completely filled, again stability is high. Next, lanthanide contraction. It is observed that in lanthanide series there is progressive decrease in the atomic and ionic radii with increasing atomic number. This regular decrease with increase in atomic number is called lanthanide contraction, which is due to the weak shielding of f orbital. Here it is 4f orbital. These f orbitals are unable to counterbalance the effective increasing nuclear charge. So, the size keeps on decreasing with increase in atomic number. Now, consequences of lanthanide contraction. Since the lanthanides show similar properties, separation becomes difficult. Because of lanthanide contraction, separation is made easier. Separation of lanthanides made easier. Basic strength of hydroxide decreases from left to right along the series. Similarly, second and third transition series, that is 4D and 5D series, are having similar atomic radii. 4D and 5D series having similar atomic radii. Next, complex formation. As D block elements, lanthanides do not show much tendency to form complexes due to low charge density because of their size. However, the tendency to form complex and their stability increases with increasing atomic number. The first few members of the series are quite reactive like calcium. With increasing atomic number, their behavior becomes similar to that of aluminium. So, we can see this is lanthanide element is denoted like this. So, all these reactions are similar to aluminium. With sulfur, sulfides are formed, nitrides, carbides, hydroxides, halides, and with acid, hydrogen gas is liberated. With oxygen, oxides are formed. These are the reactions of lanthanides. Next, we will move on to actinides. So, the elements which follow actinium are actinides, that is thorium to lawrencium, 14 elements. Electronic configuration is written like this: radon 5F 0 to 14, 6D 0 to 2, 7S2. This is the general electronic configuration of actinides. Again, just like lanthanides, we also have to note the electrons present in S first to write the electronic configuration. All have in the S orbital 2 electrons in the S orbital, and in D orbital 1 or 2 electrons are there. Here 1, this is actinium D1 configuration. Then curium Cm, then lawrencium, and this one neptunium, and one more is there, that is this protactinium. So, to keep these variations in mind, you can use some mnemonics, you can create your own, or else by their names itself you can Keep them in mind. So all these show D1 configuration, and we have in thorium D2 configuration, in thorium D2 configuration. So remaining show D0 configuration. So by these points you can write electronic configuration of any element. Next, oxidation state. The dominant oxidation state of these elements is +3. Besides +3, they show +4 also, and +4 for thorium to +5, +6, +7. Like this oxidation state varies. Melting and boiling point, they have high melting and boiling points like lanthanides, but don't show any regular trend with increasing atomic number. All actinides except thorium and americium have high density. The actinides have lower ionization enthalpies as compared to lanthanides because 5F is more effectively shielded from nuclear charge than 4F. So actinide contraction is more effective than lanthanide contraction. Magnetic behavior, all actinides are paramagnetic in nature, that is due to the presence of unpaired electron. Next, all these elements are radioactive in nature, and radioactivity increases with increase in atomic number. Next, we will move on to chemical behavior. The ability of actinides to exist in different oxidation state has made their chemistry more complex. Moreover, most of these elements are radioactive, and the study of their chemistry in the laboratory is difficult. They react with boiling water to give a mixture of oxide and hydride. They combine with most of the non-metals at moderate temperature. All these metals are attracted by HCl, but the effect of HNO3 is very small due to the formation of a protective oxide layer on their surface, just like aluminium and chromium. Now we will move on to the questions part. First question, which one of the following ions has electronic configuration argon 3d6? Atomic number is given. We have to see which option shows argon 3d6. Now, nickel is 4s2 3d8, 4s2 3d7 for cobalt. For iron it is 4s2 3d6. This is 4s2 3d5 for manganese. Now nickel 3 plus means we have to remove 3 electrons, 2 here, 1 here, so this is 3d4. Mn3 plus, so Mn3 plus is 3d4, and nickel 2 here, 1 here, we remained with 3d7, so this is 3d7. Nickel is 3d7. Next Fe3 plus, Fe3 plus 2 electrons from here, 1 electron from here, that is 3d5 we remained with. Cobalt 3 plus, again cobalt 3 plus 2 electrons are removed from here and 1 electron from here, and we remained with 3d6. So the answer is cobalt. Argon 3d6 is given by The option D. Option D. So answer is cobalt 3 plus show argon 3d6. We'll move on to the next question. The number of d electrons in Fe2 plus is not equal to the number of electrons in which of the following? That is, first we should check how many number of electrons are present in Fe2 plus. So that is 4s2 3d6. Easier way is 4s2 3d6, like this you can write the electronic configuration. Now Fe2 plus we have to make, means electrons are removed from outermost orbital, s orbital, 2 electrons are removed. We remain with 6 electrons in d orbital. Fe2 plus contains 6 electrons in d orbital. Now we will check the number of electrons in these options. So I will write S, 1s, 2s, 2p, 3s, 3p, 4s, 3d. We will allot the electrons. Magnesium 12, here 2, 6, 2. So this is magnesium over. S electrons are 2, 6 electrons. Now question is not equal, so this is not the answer. Next we will move on to chlorine. 2, 6, 2, 5. And p electrons we have to check. Here 6, here 5, that comes 11, not equal to 6 electrons. We will move on to this d electrons in Fe. D electrons in Fe is 4s2, 3d6, d electrons 6, and we will move on to this. Here it is 10, 2, 6, and p electrons is 6. Not equal to, this is 6, this is 6, this is 6, and only this option has 11 electrons, and 11 electron is, answer is B. Answer is B. So while reading the question, you should read the question correctly. Not equal to. So all the option has 6 electrons in their respective orbitals. Only option B is having 11 electrons. We'll move on to next question. 4 successive members of the first row transition elements are listed below with their atomic numbers. Which one of them is expected to have highest third ionization enthalpy? Now for the removal of first electron, the energy required is first ionization enthalpy. For removal of second electron, second ionization enthalpy. Removal of third electron, the energy associated is third ionization enthalpy. Now we will write first the electronic configuration. This is 3d6, 4s2, 3d4. Now here variation is there, 3d5, 4s1. This is 3d5, 4s2, and this is 3d3, 4s2. Now all these elements should be written in the +2 state, because we need ionization enthalpy for removal of third electron. So 2 electrons should be removed here, So we will remain with 3d6. Here 2 electrons. We remain with 3d4. Here 2 electrons remain with 3d5. And here 2 electrons we remain with 3d3. Now when we look at this configuration, to remove third electron, this is highly stable state, half filled. So to remove electron from here, the energy required is highest. So answer is C. Answer is C. We will move on to next question. The aqueous solution containing which of the following ions will be colorless? Will be colorless. Now, color is obtained by the presence of unpaired electron. If the ion is in D0 state or D10 state, then such substances are colorless. Now we have to check which is colorless. So which is in D0 state or D10 state, that we have to check. Scandium 3 plus 21, scandium is, that is 21 is 3D1, 4S2, 3 plus state, removing all the electrons, we get 3D0. So this is the answer. We will check in the remaining also. This is 4S2, 3D6, 2 plus means here there are unpaired electron, 4 unpaired electrons are there. Titanium 3 plus, 3D2, 4S2. This is after removing 3 electrons we get 3D1, 1 unpaired electron. Next Mn2 plus, 3D5, 4S2. 2 plus means 2 electrons we have to remove, and here we have 5 unpaired electrons. So the colorless with the D0 configuration is scandium 3 plus. So A is the answer. A is the answer. We will move on to next question. Which of the following statement about the interstitial compound is incorrect? Check the options. They retain metallic conductivity, they are chemically reactive, they are much harder than the pure metal, they have higher melting point than the pure metal. Now interstitial compound, just we have seen, when small atoms are treated with transition metals, the lattice points where there is hole, they are occupied by these small atoms, so they become harder than the pure metal. Since they are harder, melting point increases and they retain metallic conductivity. Metallic conductivity is retained by interstitial compound because for conductivity electrons are responsible. So metallic conductivity is retained, but chemical reactivity, they are chemically reactive. Reactivity decreases, they becomes chemically inert. So the answer is B. Interstitial compounds are obtained when small atoms are fit into interstitial space of lattice metals. These retain metallic conductivity. They resemble parent metal in chemical properties but differ in physical properties like hardness, melting point, etc. So answer is B. Next question. The d electron configuration of Cr2 plus, Mn2 plus, Fe2 plus and CO2 plus are d electronic configuration is given. For Cr2 plus it is D4, for Mn2 plus it is D5, for Fe2 plus it is D6 and for cobalt 2 plus it is D7. Which one of the following will exhibit minimum paramagnetic behavior? Again, paramagnetic behavior is shown by the presence of unpaired electrons. Now, Minimum means minimum number of unpaired electrons should be present in the ion. Now chromium 2 plus, the electronic configuration is 3d4, 4s2. For manganese, it can be written as 3d5, 4s2. For iron, 3d6, 4s2. And for cobalt, 3d7, 4s2. Now chromium 2 plus, these electrons are removed. Mn2 plus, these electrons are removed. Fe2 plus, these two electrons are removed. CO2 plus, these two electrons are removed. Now 3d4, all the 4 electrons are unpaired. 3d5, all the 5 electrons are unpaired. 3d6, here 4 electrons are unpaired, 6th one is getting paired, so we remain with only 4 unpaired electrons. And here 7th one also gets paired up, so only 3 electrons are unpaired. So minimum paramagnetic behavior is shown by 3 unpaired electron containing ion, and that is CO2 plus, and the options are given in complex ion form. CO2 plus is present in option number B. So B is the answer. Answer is B. Cobalt 2 plus ion is showing minimum paramagnetic behavior. So here see D4, 4 unpaired electron, D5, 5 unpaired electron, D6, here electron is pairing and 4 unpaired electrons are obtained. D7, here 2 electrons get paired up, 3 electrons remain unpaired. So magnetic moment can be calculated based on this, but for us number of unpaired electrons are enough to explain the minimum or maximum paramagnetic character. Next we will move on to identify the incorrect statement. Identify the incorrect statement. So we will see the first option. The transition metals and their compounds are known for their catalytic activity due to their ability to adopt multiple oxidation states and to form complex. This is correct. Second option is interstitial compounds are those that are formed when small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of the metal. This is also correct. The oxidation states of chromium in CrO4 minus and Cr2O7 minus are not the same. We'll check this. CrO4 minus, Cr2O7 minus. So chromium oxidation state, we'll take it as X plus oxygen minus 2 into 4 equal to minus 2, and X is equal to 8 minus 2 is 6. Here 2x plus minus 2 into 7 is equal to minus 2. 2x is equal to minus 14 plus 14 minus 2 is 2x is 12, x is 6. Here we get oxidation state of chromium in both the ions as 6, but here this is given not the same. So this is incorrect. This is incorrect and this is the answer. Now we will check here. Cr2 is stronger reducing agent than Fe2 plus in water. This is also correct. So the answer is C. Answer is C. C is the answer. The oxidation state of chromate and dichromate ion. Oxidation state of chromium in chromate and dichromate ions are not same. That is incorrect. They are same. Next, calculate the calculated spin only magnetic moment of Cr2 plus ion is. The options given are 4.9, 5.9, 2.8, 3.87. Now, chromium 3d5, 4s1, chromium 2 plus means we have to remove 2 electrons. From here we remain with 3d4, 1 from here, 1 from here, 3d4 we remain with, means they contain 4 unpaired electrons. 4 unpaired electrons. Chromium 2 plus contain 4 unpaired electrons. Now, if number of unpaired electrons in an ion is 1, the magnetic moment is value we get is 1 point something, 2 means 2 point something, 3 unpaired electron means we get 3 point something, 4 means we get 4 point something, 5 means we get 5 point something. If we substitute this in this formula, we are getting like that only. So instead of while studying you can solve and check, in the exam you can directly do. So the answer for this is 4 unpaired electrons, so magnetic moment is 4.9 Bohr magneton. So the answer is 4.9. See, mu can be calculated like this, and if you substitute and simplify you get 4.9 Bohr magneton. So chromium 2 plus 4 unpaired electrons, 3d4 configuration. So answer is A. Now similar type of problem which is asked in a different way. Magnetic moment of 2.84 Bohr magnetic moment 2.84 Bohr magneton is given by atomic number which atom with atomic number this. So the options are Ni2 plus, Ti3 plus, chromium 3 plus, cobalt 2 plus. So again we have to check the magnetic moment value is 2.84, so N should come around 2, N should be equal to 2. So we have to check out of these 4 ions which is having 2 unpaired electrons. So here it is 4s2, 3d8, nickel 2 plus means these 2 electrons are removed. Titanium is 4s2, 3d2, titanium 3 plus means here 1 electron remains, so you have 1 unpaired electron. In this we get 6th, 7th, 8th, 2 unpaired electron here we get. And chromium, this is 4s2, 3d4, chromium 4s1, 3d5, chromium 3 plus we have to get 1 electron is removed from here, 2 electrons from here, we remain with 3d3, 3 unpaired electrons. Cobalt is 4s2, 3d7 and cobalt 2 plus state we require. These 2 electrons are removed and here 3 unpaired electrons we get. So now the magnetic moment is 2.84. It should contain 2 unpaired electrons. So the decimal point, the digit before the decimal point indicates the number of unpaired electrons. So 2 unpaired electrons containing ion is the answer for this. So that is option A, which is nickel 2 plus. Option A, which is nickel 2 plus. Next, When neutral or faintly alkaline potassium permanganate is treated with potassium iodide, iodide ion is converted into X. X is, just we have seen in the theory, in faintly alkaline medium, potassium permanganate is converted to iodate. So, C is the answer. Sorry, potassium iodide is converted to potassium iodide is converted to iodate is the answer. When neutral or faintly alkaline potassium permanganate is treated with potassium iodide, potassium permanganate is converted into manganese dioxide, while iodide ion is converted into iodate. So the reaction is like this. So C is the answer. Next question. Which of the following does not give oxygen on heating? See the option. Potassium chlorate, oxygen rich compound. Zinc chlorate, oxygen rich compound. Potassium dichromate, oxygen rich compound. Whereas this is producing nitrogen gas, whereas remaining three, A, B, C, they produce oxygen. So the answer is D, ammonium dichromate. So you can go through the reactions. Here only we are getting nitrogen, and else in all the other reaction we are getting oxygen. Question is does not give oxygen, so the option is this. Next, name the gas that can readily decolorize acidified potassium permanganate solution. Acidified potassium permanganate acts as oxidizing agent. So this is oxidizing agent. This is neither oxidizing nor reducing. This is reducing agent, dehydrating agent. So the answer is B, sulfur dioxide gas readily decolorize acidified potassium permanganate solution. Next question is HgCl2 and I2 both when dissolved in water containing iodide ions, the pair of species formed is. Now the options are HgI2I3 minus, HgI2I minus, HgI42 minus, I3 minus, Hg2I2I minus. Now we are taking HgCl2 and I2 both dissolved in water containing I minus ion. These are dissolved in water containing I minus ion. These two react forming I3 minus, that is I2 I minus react to form I3 minus. These two react forming Hg I2. First we will check this I3 minus. So either this option or this option. Now since HgCl2 reacts with I2 forms HgI2, but the amount of I minus is not mentioned. When it is not mentioned, it is taken as excess. So this further reacts to form HgI4 2 minus. So these are the species formed. So this is not the answer. This is the correct answer. So this is the correct answer. So I2 and I minus, I3 minus is formed Then this reacts with Hg2 plus with I minus forms HgI2. HgI2 further reacts with excess of iodide to form HgI42 minus. So C is the answer. We'll move on to next question. When copper is heated with concentrated HNO3, it produces. Now copper when treated with dilute HNO3, one type of gas is formed. With the concentrated HNO3, one type of gas is formed. So the answer is CuNO3 twice NO2. Answer is NO2. So nitric acid acts as oxidizing agent. With the dilute HNO3, NO is produced. With the concentrated, NO2 is produced. Next question. Which of the following processes does not involve oxidation of iron? Now rusting of iron sheet. It is oxidation process. Iron with the oxygen in the presence of moisture, iron oxide is formed. Here oxidation state is 0. Here it is +3, which is oxidation. Decolorization of blue copper sulfate with the Fe. Decolorization of blue copper sulfate by iron, we get ferrous sulfate. So this is also 0 to +2, again oxidation. Question is, does not involve oxidation. Formation of FeCO5 times from Fe. This is FeCO molecules which forms FeCO5 times. Here oxidation state is 0, here also 0, and this does not involve oxidation. So this is the answer. We'll check the last one also. Liberation of H2 from steam by iron at high temperature. This is also oxidation. So iron by steam, again we get ferric oxide, where 0 oxidation state is converted to +3, which is oxidation. So formation of FeCO5 is the answer. C is the answer. Next we will move on to, which one of the following elements with the following outer orbital configuration may exhibit the largest number of oxidation state? Now oxidation state, we get different oxidation state by the participation of electrons in bond formation, that is by Ns or N-1 d electrons. So maximum largest number of oxidation state is obtained by both Ns and Nd electron when they get participate in bond formation. So just here 2, 2, 4 electrons, 3, 5, 5, 1, this is 7, maximum largest number of electrons is shown by this 3d5, 4s2, answer is D. Next we will move on to next question. The reaction of aqueous KMnO4 with the H2O2 in acidic solution gives. We have seen different reactions of oxidizing property of potassium permanganate, that is KMnO4 in acidic medium gives Mn2 plus ion, either this or this. Now H2O2 is converted to O2, so the pair of species we get here is B. B is the answer. The reaction of aqueous KMnO4 with H2O2 in acidic medium is Mn2 plus ion with oxygen. In the above reaction, KMnO4 oxidizes H2O2 to O2 and itself get converted to MnO4 minus, then reduced to Mn2 plus, which is in the form of MnSO4. Hence aqueous solution of KMnO4 with H2O2 gives Mn2 plus and O2. Next question. The most durable metal plating on iron to protect against corrosion is. This depends on SRP value. Now, SRP value of nickel, tin, copper, zinc, iron are like this. That is nickel, tin, nickel, copper, zinc, iron. Now, zinc has less reduction potential than iron, so zinc plating is done, which is called as galvanization. Zinc is commonly used for covering iron surfaces. The process of covering iron with the zinc is called galvanization. If some scratches, even if occur on the surface, the protective zinc film on the which is coated on iron, the iron will not get rusted. This is due to the fact that both zinc and iron get exposed to oxidation, but zinc undergoes oxidation in preference to iron because the reduction potential of zinc is lesser than that of iron. So, zinc coating is the best and durable method for protection of iron. So, answer is D. Next, we will move on to the electronic configuration of EU. Atomic number is given GD, TB. So, we have to write, we have to choose the correct electronic configuration. Now, since all these elements are lanthanide elements, the noble gas in each one is inner core is xenon. Now, S electron in all the elements are 2. So, here we have 2, 2, 2, all. S electrons are 2. Now, first we have to check D electrons. So, EU 63, GD 64, TB 65. We have first seen that the D electron in GD is 1, that is La, Ce, GD, Lu. These elements show D1 configuration. So, for GD, D is 1. First, what you have to do? 6s 2 electrons, 5d 1 electron. For GD I am writing down 5d 1 electron. Then here we have xenon. So, atomic number is 54, 55, 56, 57. 57 means 7 electrons are left, which is filled in f orbital, 4f7 it becomes. So, this is the electronic configuration of G, the gadolinium. Next, TB, again xenon 54. Since D1 configuration in this element is not included, so D is 0, S is 2, D is 0, xenon is 54. Now, 54, 55, 56. 56 means 9 electrons are remaining for 65. So, you get here 4f9, this electronic configuration. Next, for this europium, again 6s2 electrons, 6s2 electrons, and in this list there is no EU, so it is D is 0. Here also D is 0. So 54, 56, 56 means minus 63, 7 electrons. So 4f7 you get. So like this you can get the electronic configuration. Now check the correct answer. Answer is C. This is for 4f7, 6s2. Then this is for GD, 5D1, and this is for 4f9 TB. This is the correct answer. So, if you keep this in mind, you can write electronic configuration of any element, because s orbital in all the lanthanides are being occupied by 2 electrons. Next, the reason for greater range of oxidation state in actinoids is attributed to. Now, greater range of oxidation state. Now, the radioactive nature of actinoids. No. Actinoid contraction, that is related to size. Then for 5F, 6D, 7S levels having comparable energy, we'll check. 4F and 5D levels being close in energy. Now, since the question is on actinoids, 5F orbitals are filled in actinoids, this is not the answer, this is the answer. So, C is the answer. The reason for greater range of oxidation states in actinoid is attributed to the 5F6D, this is 5F6D, and 7S levels having comparable energies. The 5F orbitals extend into space beyond 7S and 6p orbitals and participate in bonding. This is in direct contrast to the lanthanides, where 4f orbitals are buried deep inside the atom, totally shielded by other orbitals and thus unable to take part in bonding. Next question is, which of the following lanthanoid ions is diamagnetic? What we have to do? Diamagnetic means unpaired electrons are not there, means they are diamagnetic in nature. Now in these ions we have to check which contains paired electrons, does not contain unpaired electron. Now cerium electronic configuration is this, 2 plus means these 2 electrons are removed, it contains 2 unpaired electrons. Samarium, 2 plus means these 2 electrons are removed and it contains 6 unpaired electrons. Then europium, 2 plus, these 2 electrons are removed, 7 unpaired electrons, and ytterbium, this is the electronic configuration. If we remove these 2 electrons, we get Yb2 plus, which does not have any unpaired electron, no unpaired electron, all the electrons are paired. So this is diamagnetic in nature. So the answer is D. Answer is D. All the electrons are paired, remaining options are having unpaired electron. Next question is, which of the following ions will exhibit color in aqueous solution? Will exhibit color in aqueous solution. Now color is observed by absorption of radiation. So when the ions contain unpaired electron, they undergo transition, DD transition, and when they come back, electrons are coming back to the lower state, energy is emitted, that is observed as color. Now, the options, we have to check which contains unpaired electron. So, we will see lanthanum 3+, lanthanum 3+, no unpaired electron, no unpaired electron. Titanium, there is one unpaired electron in titanium 3+, lutetium, again no unpaired electron, scandium 3+, no unpaired electron. So, answer is titanium 3+, which has one unpaired electron. This is the answer. B is the answer. Next, correct order of ionic radii of Y3+, La3+, Eu3+, Lu3+ is, atomic number is given, and we should now have a knowledge of placement of these elements in the periodic table. These are lanthanoid elements, and this is included in the series, the first element, and this is D block element which is above lanthanum. So, the position is yttrium, lanthanum, europium, lutetium. Y, La, Eu, Lu, all are in +3 state. Now, along the lanthanoid series, the atomic radii, ionic radii decreases. Now, in the periodic table, as we move from top to bottom, what happens? Atomic radii, ionic radii increases. Atomic radii, ionic radii increases. As we move this side, radii decreases. So, the correct option is D is the correct option. So, just we will have from top to bottom, atomic radii increases. So, this is smallest. From left to right, if we move, radii again decreases. So, lutetium is having smaller size than europium. In turn, lanthanum is having smaller size. So, this is the answer. So, these are few questions from the previous year question papers. So, students solve more questions, read the chapter thoroughly, have a good knowledge about the concepts. If you know the concepts correctly, then you can answer any questions. Thank you.